Hello again, this is Dr. James Camp from Lee College in Baytown, Texas, and this is my commentary on Chapter 2 of Big C++ by K. Horstmann, in which we talk about data types and mathematics. First, we're going to talk about variables. Okay, um, a variable is used to store information. Uh, each variable, until we get to arrays and structs and such, can contain one piece of information at a time. The book likes to use the analogy of a parking garage in that each parking space can hold one car at a time. In some garages, none that I'm familiar with, each parking space is identified individually. In this picture here, you have J053 and J054, and each parking space is then able to contain one particular car, just as a variable can contain one particular value. And most importantly, each parking space has a size, okay? Just as variables in C++ have a type. They can contain an integer or a floating point number or a character, but they can only contain one of those things. You don't resize your parking garages. You don't resize your parking space to fit a bus into a space that's designed to fit a car. Okay, so computer memory is a long chain of parking spaces for binary numbers. So imagine we have the memory locations A001, A002, A003, and A004. Each of those locations holds a byte of memory, that is 8 bits, okay? And each bit is either a 1 or a 0, as you can see in this depiction here. All 4 of those actually are necessary. All 4 of those memory spaces are necessary to hold a 32-bit integer. So the integer type variable myNumber, declared in C++ as int myNumber, points to the very first of these 4 memory boxes, but it actually owns myNumber refers to all 4 of those memory boxes put together in some sort of way. When you declare a variable, C++ needs to know how to find the memory location. So myNumber, a unique name for the variable, and it has to be told what it's going to find when it looks there, how big the memory location is that it's looking at, and how to interpret the information that it finds there. So that's what the variable type int means, is look for a sequence of 4 memory boxes and interpret the binary data there as a 32-bit integer. Okay, variables in C++ are not just used, they have to be declared or defined before they can be used. And there are 3 parts of a variable definition that are shown here at the top of this screen. In blue, when creating a variable, the programmer specifies the type of information to be stored. In this case, it's an int for an integer. There's also char for character, double for double precision floating point, bool for boolean, that's a true-false value. Those are the basic C++ types. There are also more complex types like a string that can be used in some cases. In green, the second part of a variable definition, the programmer has to choose a good name for the variable. My variable is not a very good name for this variable because we really don't know what it's going to be used for from that name. Weight in pounds and height in inches are much better variable names because you can tell at least what the meaning of the the number held in that variable is, as opposed to if you just said that a person had attribute 1 and attribute 2. Well, then that wouldn't tell us what each of those attributes means. Okay, and finally, in red, unlike a parking space, a variable is often given an initial value. Parking spaces are taken to be initially empty, and then they get filled when someone parks there. But variables always have something in them. In C++, when you create a variable, if you just say int my variable semicolon, my variable will point to a memory location, and that memory location will have whatever random gobbledygook was in that memory location to begin with. It will be uninitialized. So my variable might hold 2,245, and you wouldn't know that. On the other hand, if you type equals 42 at the end of your variable declaration, you know for sure that 42 is the initial value of my variable. Now 42 is not a very reasonable initialization value. Usually people would initialize an integer to 0 or maybe to 1, something that indicates that it hasn't really been used yet, as opposed to initializing it with a value, though sometimes you know for sure that you want cans in the pack to be 6 to start with, because you're giving somebody a fresh unopened 6-pack of cans. Okay. So here is an example of a variable definition that's done well. So it's an int. It means it contains an integer data. It has the name cans per pack, which is a useful descriptive variable name, and it has an initial value equals 6, which that tells us immediately that this is a 6-pack of cans, and the initial number of cans in the pack is 6. Here are a few more variable definition examples. You don't have to initialize with a literal number. You can initialize with a mathematical expression. So int total equals cans plus bottles. You cannot initialize an int variable with a string of text. So putting 10 in quotes turns that 10 from a literal number into a literal string, and that is not compatible with an int. You can define int bottles without initializing it, which means as long as you then read in a value from the keyboard or assign it a value soon down the road, you're fine. But if you then forget to assign it a value later, like I said, it will have whatever random set of data was in that memory location to begin with. Finally, you can declare 2 values on the same line. You can declare 3 or 4 or 5 or 6 values on the same line just by putting commas between them. Not shown here, you can even initialize values while listing multiple on the same line. So you could have int cans equals 6, bottles equals 2. As we've said before, variable names should explain the purpose or the contents of the variable. A lot of people like trying to save themselves keystrokes by abbreviating can volume to CV or just vol, which tells me it's a volume maybe, but not that it's associated with a can. Or, in today's integrated development environments like Visual Studio and Xcode, there's a lot of stuff built in that will help you complete your variables. You start typing can and it gives you a list of variables, and you hit tab and it will finish out your variable name for you. So there's really no reason to shorten your variable names to the point where they're no longer meaningful. It's much better, and you will get much more credit in this class if you give all of your variables self-explanatory names. Okay, rules for variable names. They must start with a letter. They may start with the underscore character, but most people, by convention, do not do that, except in very specific cases that we're not going to get into in this class. The remaining characters must be letters, numbers, or again, the underscore character. You can't use any of the special symbols on the keyboard, the ones that you get by hitting shift and any of the number keys, or any of the punctuation marks or anything like that. You can't put spaces inside a name. That's why they allow the underscore character, so that you can, can volume has an underscore character to tie the word can and the word volume together. Variable names in C++ are case sensitive. Actually, that's true in almost every programming language I've ever used. All the modern programming languages are case sensitive. So can volume and can capital V volume are different variables. Since this can lead to some confusion in your code, C++ programmers tend to use only lowercase letters in variable names. This is different from other programming languages like Java or C#, where people tend to use capitalization in particular patterns to indicate things about their variable names. But the C++ convention is to use only lowercase letters. And finally, it should go without saying that you can't use reserved keywords such as type names, double, or programming keywords return as names. Those words have special meanings to the compiler, and if it sees you trying to use it as a variable name, it won't know what to do with it. It won't compile. Here are a couple of examples of variable names. The first three work, the last four don't. It's worth noting in the second example that in much of mathematics, you may have taken algebra and geometry and learned to use single letters as variable names. This is allowable in C++, but unless those single letter names have very clear meanings, it's better to spell out names for your variable. If you're working in, writing a program for physics, and T always means, lowercase t always means time, and capital T always means temperature, and you think you can get away with that, fine. But it's probably better in programming, from a programming standpoint, to spell out the word time and the word temperature, or at least temp. Though temp could also mean temporary, so temperature is a better variable name there. Okay. Computers think of numbers in a few different types when they're trying to interpret a string of binary digits in memory. One way is to interpret it as a Boolean. That is, it has the value 0 or not 0. Okay. Where 0 is false, and anything other than 0, any value other than 0, is true. Now, if you define the value as a Boolean variable, it's either going to store 0 or 1, where 0 is false and 1 is true. An integer is a positive or negative whole number. That is a number with no fractional part. So minus 21, 0, 42, 320, 256. I could keep listing whole numbers if I really wanted to. And then there are floating point numbers. These are what we call real numbers, numbers that have a fractional part, even if that fractional part is .0. Okay. 50.0 is a floating point number because we know that it has a 0 after the decimal point. Notice that negative 0.3 and 3.14159 are sort of conventional floating point numbers, but 6.02 E23, Avogadro's number, is also a floating point number because in this case, not only is there something past the decimal place, but the decimal place is actually floating because it's multiplied by a power of 10. That's read as 6.02 times 10 to the 23rd. And the last one here is read as 1.45 times 10 to the negative 10, so that's a very, very small number. Each number type also comes in sizes. Well, Boolean doesn't. Boolean is just 0 or 1. But integers, long time ago, when you had computers that had a shortage of memory, you would have a short integer, which was 2 bytes, and an int, which was 4 bytes, and a long, or maybe short was 1 byte, and int was 2 bytes, and long was 4 bytes, and long was 8 bytes, or something like that. It actually was never defined in the C++ specification how big each of these was supposed to be. Today, int is usually taken as a 4-byte or 32-bit integer, and long is also taken as a 4-byte 32-bit integer, and long, and extra long, would be an 8-byte 64-bit integer. Similarly, floating point is there's a float, which is a low precision, which was designed to conserve memory in computers where memory is tight. There is a double, which is double precision, and then there's long double, which is double that. Today, a double is typically 8 bytes or 64 bits, which is more than enough room to store most floating point numbers of interest and to keep a decent number of significant figures with them. Okay, now when you write a number to assign it to a variable, writing the number out in code is called a number literal. Sometimes it's called hard coding the number. Okay, each number literal has to be interpreted by the compiler as either an int or a double. Why not a float, you say? Why not a long? Well, somebody whoever made up the C++ standard decided that numbers were either going to be ints or doubles. There are ways to specify that you want something to be interpreted as a long or a float or something. We're not going to get into that in this class, but you can look them up. It involves putting a letter after the number, like 21L, I believe, becomes a long, or 3.14F becomes a floating point, a float. There are rules for writing literal values and how C++ interprets them. Okay, if it has no fractional part, it's going to be interpreted as an int, whether it's positive, negative, or 0. If it has a fractional part, if it has a decimal point and something after the decimal point, it's going to be interpreted as a double. Even if the thing after the decimal point is a 0, C++'s bias is to make that a double. If it has an exponential in it, and an e, it's going to be interpreted as a double. So 1e6 is actually an integer, 1 followed by 6 zeros, but because of the way we specified that as 1e6, it's going to be interpreted as a double. Finally, a couple of common errors. Do not use commas to separate thousands and millions and things like that. Just does not work in C++. And do not write numbers out as fractions, as mixed fractions, 3 1/2. Instead, estimate a decimal notation 3.5 for that. Okay, so take a moment and see if you can guess what C++ type would be assigned to each of these number literals. It's not that hard because we put them in order. This first one is an int because it has no decimal point. The next one is also an int because it has no decimal point. The next one does have a decimal point, and so it will be a double whether the decimal point is 0.14 or 0.0. The fifth one has an exponential in it, and since it's exponential to a negative number, it will be less than 1, so it's a fractional number as well. So however you look at that, that's going to be a double. And then, of course, here is an error. Somebody put commas in there, and then this last one is an error. Somebody tried to write a mixed number fraction. Okay. The contents in variables can vary over time. That's where they get their name, variable. Variables can be changed by assigning them a value. My var equals 42. Or using the increment or decrement operators, plus, plus, or minus, minus. Or by inputting into them cn greater greater my var will read a value from the keyboard and store it in my var. Now, if you don't want the contents of a variable to vary, you make it a constant instead. And in C++, we have a handy const keyword that allows you to do that. Const int cans per pack equals 6 means that now cans per pack is no longer something that can vary. We can't take cans out of the pack. Now it's a constant defining how many cans can fit in a pack, say. And so that is going to be 6 forever and ever. Now, because of a tradition inherited from standard C, where all constants are pound defines, constants are often written in all caps in C++ as well to remind you that they are constants and to make them look visually different from other variables, from variables. So this is how an assignment statement works. Cans per pack equals 8 changes the value of cans per pack from whatever it was before to it now is 8. So we've now got an 8-pack of cans instead of a 6-pack of cans. The previous value is just replaced. There's an important difference between a variable definition and an assignment statement. A variable definition starts with a type name, int, cans per pack equals 6, and that creates a new variable that has never existed before. Cans per pack equals 8, the second statement here, is just an assignment statement. It does not create a new variable, it just reassigns the variable cans per pack to now have 8. The first statement is the definition of a can of cans per pack, and it creates the variable, and that can only happen once per program, or at least once per block. We'll talk about what code blocks are further on in the semester. The second statement is an assignment statement, and it just replaces the contents of an existing variable. It does not create a new one. And the same variable can be reassigned several times in a program. In fact, we encourage you to, because that's what variables are for. Okay. Now, it may confuse you that the equal symbol is used for assignment, where you've been learning all your life in algebra class that equals means the left-hand side is going to equal the right-hand side, and then you can solve both sides of the equation and get some sort of number out of it. This is programming, not algebra class. Equals is not a statement about an equation. It's an instruction to the computer to do something. It's going to copy the value from the right side of the equal sign into the variable on the left. Okay, the left-hand side can only be a single variable name. The right-hand side can be whatever complicated math expression you want. And all of that said, if the phrase var equals var plus 2 confuses you, you can start thinking of a single equal sign in C++ as an arrow instead. It takes whatever's on the right and stuffs it into the variable on the left. Okay, so just a couple of examples of assignments. Counter equals 11 is going to set the variable counter to 11. Counter equals counter plus 2. Note that it doesn't matter that we have counter on both sides. We're going to take whatever's on the right side, counter, which is already 11. We're going to add 2 to it and get the value 13. And then we're going to stuff that value into the variable on the left. So counter is now set to 13. Okay. Another good reason for using constants, switching gears here, what if you said that the volume, the total volume of all your bottles is the number of bottles times 2? Well, what does that 2 mean? Are we doubling the number of bottles? No, 2 is supposed to mean the volume of a bottle. We're using 2-liter bottles. So if we use a constant and we say const bottle volume equals 2, and especially if we then leave a comment there that says 2 liters, then we can use the phrase double volume equals bottles times bottle volume, and that's much more clear about what we're doing with that. We're not doubling the bottles, we're just multiplying by the volume per bottle. Okay. Another good reason for using constants, what if we had bottles times 2 is bottle volume and cans times 2 is can volume? Now we have 2 literal 2's that probably mean different things, because I've never seen a 2-liter can, so 2 must mean 2 ounces or something else. 2 pints, maybe? I really don't know. Now that we have the idea that these 2's may mean different things, and they're right next to each other in the code, and anybody who tries to read this segment of code is going to get very confused. Programmers call this practice of dropping number literals into your code without any kind of explanation, they call that magic numbers. Okay, magic numbers make your code hard to understand. For somebody who's never read it before, they make it hard to debug, because you might go back through here and say, okay, what was I thinking? Why is there a 2 there? And it's much harder to maintain, because suppose that the number 2 appears hundreds of times through your program, which is quite possible, because you have things where you are doubling the number of things, and you have other things where the volume is 2, and you have other things where so you need to change every place where 2 is being used as a bottle volume to 3. Okay, you can't do a find and replace and just change some of the 2's. So you're going to have to read through your entire code and change just the ones where the 2 means a volume of a bottle to 3. Suppose instead you had const double bottle volume equals 2, and you could change it to const double bottle volume equals 3. Now you're able to change one line of code and effectively maintain the entire source code for your project. Okay, and that also brings me to the idea of documenting your code. It is important to explain, because you will not be the only person who ever reads your code, and you will not always remember what you were thinking when you wrote your code. It is important to put some documentation inside your code. Okay, there are 2 ways of documenting code. The first is called self-documenting, and the second is called comments. And these are not mutually exclusive. You can do both. But consider calculating somebody's body mass index. If you have weight in kilograms equals weight in pounds times kilograms per pound, height in meters equals height in feet times meters per foot. And then BMI is weight in kilograms over height in meters squared. You can tell just by looking at those variable names what's going on here. Maybe you need to put in a comment explaining that BMI is weight in kilograms divided by height in meters squared. But generally speaking, you can tell what the person was thinking just from looking at their variable names. In other cases, it's not so easy to understand where a number comes from. And so comments are explanations for your human readers that other programmers or me, your instructor. The compiler is going to ignore anything you type in a comment completely. Okay. And that allows you to say whatever you need to say to explain your code, to explain what you're thinking there. There are two styles of code of comment in C++. The first is called a one-line comment. You put two forward slashes, and then everything from those forward slashes to the end of the line is going to be ignored. The second is called a multi-line comment, and that just, you start with a /* and you end with a */, and everything between those two is ignored. So this allows you to write longer form comments about what your program does, perhaps, or what a particularly long block of code is about to do, or something like that. One programming tip: these multi-line style comments can be used to do something we call commenting out code. Okay, if you have code that's behaving badly, it's not compiling, or it is compiling but it's making things go wonky, you can put a /* at the beginning of the code and a */ at the end of that code, and then the compiler will just skip over that little block of code. Why would you want to do that and not just delete that code? Well, because maybe you worked for a while to get that code the way it is, and you're sure that it's close to right, but you need to go on debugging the rest of the program, and you're going to come back and work on that patch of code later. In this case, there is no function called square, so the programmer was a little bit confused and needs to look up their C++ functions again. Okay, another side note, you may have noticed that I just used a constant called mpi in the previous page. Sometimes you need to use the math constant pi. We're going to do that for your programming break today. Well, m_pi stands for math pi. Comes from the cmath library. Okay, because it's C compatible, it's not actually a C++ constant, it's a C pound define. Also, for reasons that have never made any sense to me or anybody else I know, mpi is turned off by default when you import cmath. So to turn it on, you have to put the line pound define _use _math _defines at the beginning of your program. And when I say at the beginning, it has to be before any pound includes. So it has to come before pound includes cmath, it has to come before pound include iostream. It just has to be up there at the very, very top of your program. Pound define, use math defines. Okay, and here is a complete volume that, a complete program that tells you how much a 6-pack plus a 2-liter bottle of Coke contains. Okay, before we move on, a couple of common errors. It's fairly common to use undefined variables or to define a variable after the time when you're first intending to use it. The only problem with the code that's shown here is that liter per ounce needs to be defined before the line can volume that uses liter per ounce. Um, Another common error is to use an uninitialized variable. In this case, the programmer chose to use int bottles without setting a number of bottles. They forgot to initialize it, or maybe they just intended to set a value for it later or read a value from console input. And so int bottle volume equals bottles times 2. Bottles contains a random value pulled from memory, which is probably something quite extraordinary, like 2,342,000 or something. So when you see out bottle volume, you're going to get a completely unpredictable result. Okay. In addition to the int and double types, C++ has some other numeric types. In the floating point realm, there is float, which uses half the storage of a double, but only has about 6 to 7 significant digits and is much more subject to rounding errors. So we don't use float anymore. You scan the internet for code examples, you'll see some people who use float for examples because they think it reads better than double, I guess. But you really shouldn't use the float type for anything anymore. The third type is called long double, and that's for a quadruple precision. That ensures that you get a 64-bit double precision, but most contemporary compilers use the quadruple precision type when you ask for a double, so it's better to just use doubles for everything. Why are these numbers called floating point? It's because 29600, 2.96, and 0.0296 in the decimal world in base 10 are all the same number, 296, times a floating with a floating decimal point. The point is either 2.96 times 10 to the fourth, or 2.96 times 10 to the 0, or 2.96 times 10 to the negative 2. So by attaching a times 10 to the number, an exponent, the decimal point floats along the number. Also, in addition to the int type, C has short and long. And then there are unsigned equivalents, unsigned short, unsigned int, and unsigned long. Unsigned int is just called unsigned. And those double the range on the positive side and disallow any negative numbers. A short value uses 16 bits, which typically goes from negative 32,768 to 32,767, which is a remarkably small range, so we don't use short for very many things. This shows you the range of the numeric types. Note that a long contains 8 bytes for an integer, so it's very, very large. Why do you need long? Because sometimes the int will do what we call overflow. Okay, a 32-bit integer can hold up to 2 billion values, up to 2 billion. But let's say you need to represent the world population, which is currently like 8 billion. You would need something larger than an int. If you tried to take the population of India, which is about a billion people, and multiply it by 3, no error would be displayed, but the result would be cut off to its least significant 32 bits, and you'd get a value that is completely wrong. So 1 billion times 3 gets negative 1.29 billion because the result is larger than an int can hold, and it overflows. You could use a long instead. That would be the logical thing to do. Or you could use a double, because that has a huge range. However, with double, you have the possibility of round-off errors. What's a round-off error? Well, let's take 4.35 and multiply it by 100 to find out how many pennies we have. Um, 100 times 4.35 will be 435. But if we store 4.35 as a double variable, it'll be stored in the computer as 4349, blah, 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 blah. Okay, it'll have a rounding error. And when we multiply by 100 and then chop it off as an integer, we don't round, we just chop it off. The number we get is 434. Okay. Now, the reason for this is that computers store numbers as binary. So 4.35 is not stored as 435 times 10 to the 0. It's stored as some binary approximation of that. And when you multiply that by 100, which is also not a binary, an exact binary number, you end up getting a number that is not an exact binary equivalent of 4.35 times 100. When you then assign it to an int variable, C++ does not round it to the nearest integer, it just cuts it off at the decimal point, and so you're going to get a number that's a little bit wrong. One way is to use the round functions that are built into C++'s mathematical library. Another is to just add 0.5 before you truncate to an integer, and that is essentially a rounding procedure, because if you had 434.5 and you added 0.5, that would knock it up to 435, and you'd get the right number this time. In C++11, we added a keyword, a type word called auto, which the type is now automatically deduced from the initialization data. You cannot use this for an uninitialized variable, but you can automatically set cans to int by assigning it an int type value. You can automatically assign can volume to be of type double by giving it a double type value. So C++ has the same arithmetic operators as a for-function calculator. Star for multiplication, slash for division, plus for addition, minus for subtraction. Note that there is not an exponentiation operator. Whoever designed C way back when decided that it was not necessary to raise numbers to a power, and so we just didn't do that. And so all of the C-derived languages, C++, C#, Java, JavaScript, do not have any way to exponentiate numbers. Just as in regular algebra, star and slash have higher order of operations than plus and minus. We call that higher precedence in programming. So if A plus B over 2, B over 2 is going to happen first. You can, of course, as in algebra, you can put parentheses in your expressions to indicate that you want A plus B to happen before the divided by 2. There are increment and decrement operators. If you attach plus to the end of a variable, that's just going to add 1 to it. If you attach minus to the end of a variable, that's going to subtract 1 from it. The joke, of course, is that C++ was based on C, so it's one better than C, right? That's where C++ got its name. Okay. It's also very common to want to change the value of a variable by a certain amount that isn't 1. Okay, there are shorthand operators for this too. Num plus equals 4 is the same as num equals num plus 4. And so on for minus equals 3, times equals 2 will double a number, slash equals 10 will divide a number by 10. Dividing two integers is a dangerous operation in C++ because C++ assumes that if you're dividing two integers, you want an integer to come out of it. So if I tried to say double half equals 1 divided by 2, half will be 0. It's going to calculate the result, 0.5, and then it's going to throw away the fractional part and keep the integer part, which is 0. If you want the correct result, one of the two has to be a floating point number. So I can say double half equals 1 over 2.0, and now half is going to be what I intended it to be, 0.5. There is also an integer remainder operator, also called the modulus operator or modulo or mod. 5% 2 is going to take 5, divide by 2, throw away the answer to the problem, and keep the remainder. Okay, so negative 5% 2 is going to be negative 1. It always has the sign that the normal division would have, and then it has, but it's the remainder of that division. Worth noting that this percent operator has nothing to do with calculating percentages. It was chosen because it looks a lot like the division operator. It looks like a number divided by another number. Okay. Where does this come in handy? Let's say you want to know how many dollars and how many cents are in a collection of pennies. Okay. You obtain the dollars through integer division by 100. 1729 divided by 100 is going to give you $17. You get the number of cents by using the percent operator. 1729% 100 is going to give you the remainder, 29. And so that will set your cents, your dollars to 17 and your cents to 29. Okay. So see if you can predict the result from each of the following. If necessary, pause the video for a moment and work through it in your mind. Okay. The first one, you should have guessed 6 because that is an integer division. 27 divided by 4. We're going to throw away the floating point part of it and just keep the integer, which is 24 divided by 4 is 6. This next one of the two, 27.0, is a double, so we're going to get a double result, 6.75. The third one, 27 remainder when dividing by 4, is going to be 3. We take 24, which is an even multiple of 4, and then the remainder is 3. Negative 27% 4 is the same thing, except you're going to get a negative 3. What about 27% 10? Well, we take out 20, which is an even multiple of 10, and the remainder is 7. Finally, 27% 2 is 1. This is a very handy way to find out if a number is even or odd, is you just take percent 2. If the answer is 0, it's even. If the answer is 1, it's odd. Okay. When a floating point number is assigned to an integer, the fractional part is discarded. We've kind of covered that already. So 2.55 in normal American practice would round to 3, but C++ does not do rounding. It just cuts off the fractional part, and so price will be 2. If you want to round, you add 0.5, dollars equals price plus 0.5, and that will convert it to 3.05, and 3 is what you would get. What about this? Okay, the inside the parenthesis part is easy. 1 plus r over 100. But what about that raised to the n part? Okay, we need to pull the power function out of the cmath library, which means we need to pound include cmath at the top of our program file. The power function is set up as pow and then base comma exponent. So remember b times 1 plus r over 100 to the n. So we'll translate that as b times pow, open parens, 1 plus r over 100, comma n, close parens. Here are a couple of other mathematical expressions and how they translate into C++ code. Pay attention to the fact that there is a square root function in C++, sqrt, though you could do that by using pow a squared plus b squared comma 0.5 if you wanted to. You can get any arbitrary root by using the power function. There are some other mathematical functions in the cmath library. The major trig functions, sine, cos, tan. Log will get you the natural log. Log 10 will get you the decimal log. And in C++ 11, I believe there's also a log 2 that will get you the binary log, which is very handy for programming. And then abs of x will get you the absolute value of a number, which comes in handy all the time. So again, pause your video and try to figure out the result of each of these. Ten to the third is 100. Square root of 100 is 10. 3 minus 10 is negative 7, but the absolute value is 7. Log base 10 of 1,000 is 3. The maximum of 3 and negative 10 is 3. The cosine of pi is negative 1, and the tangent of pi over 4 is positive 1. The mpi constant is defined in the cmath library, and I told you how to activate that earlier in this presentation. Okay, if both arguments of slash are integers, the fractional part is discarded. 7 over 3 is 2, not 2.5. But if at least one of them is a double, you get a double. Never define a math formula using integer division. Okay, I have taught engineering students to program in C++ for a long time, and they always make this mistake. They'll say something like v equals 1/3 h m pi pow r squared. But if you do this, that 1/3 is going to be 1 divided by 3, which in integer division is 0. So the volume of your cone, I think this is, will always be 0 no matter what you put in for r or h. The better thing to do is to multiply by 0.33 or take 1.0 divided by 3.0, or that's probably the best thing to do. Okay, more on unintended integer division. The remedy is to make the numerator or denominator a floating point number. Okay, so average S1 plus S2 plus S3 over 3.0 is going to guarantee that you get the right expression, the right answer. Consider this expression. Can you figure out what's wrong with it? Well, the parentheses are what we call unbalanced. There's a blue pair there, there's a green pair there, and there's a red one that's not matched. And we can't tell whether that red one was intended to go around the numerator of the expression or maybe around the entire fraction as it's written there. This is very common the more complicated your expression gets. One way to do this is to count. You increase your count every time you open a parenthesis, and you decrease your count every time you close a parenthesis. And if your count is not 0 when you get to the end of the line, then you did something wrong and you need to go back and balance your parentheses. Reminder to include the proper header files. If you're not sure what header file your particular function comes from, that's why Tim Berners-Lee invented the web. There's a reference site called c++.com that makes it very easy to look up a function and find out which header it's in. A reminder to put spaces before and after each of your operators to make your math easier to read. But you don't put space after what we call a unary minus. That's just turning b into negative b. And we don't put spaces between the function name and its parentheses, so we write square root x, not square root space parens x. Occasionally, you need to store a value into a variable of a different type, or print it in a different way, or use it in integer division when you, use two integers in what you intend to be floating point division. And the way you can do that is to cast one variable to another type. Okay, so if int x is 25 and int y is 10, you can say x divided by static cast to a double of y, and that forces y to be a double and gives you the quotient you're looking for of 2.5. It says it's an older version of the cast conversion syntax. It's actually a more universal version. This works in standard C or C++ or Java or C#. You put the type name in parentheses before the value that you're intending to convert. So this would be cout x divided by parens double y. And that will again force y to be a double and give you the quotient you're looking for. Okay, so we've reached the end of this lecture. Thank goodness. It's time for a little bit of programming practice. And the program I want you to practice on is the suspension system on a car is modeled by the equation d equals cos pi t e to the t over 2. D is the displacement, how far the car moves when you hit a bump, and t is time. Okay. I want you to write a program that picks the first 7 time points, t is 0, 1, 2, 3, 4, 5, and 6, and just prints out d for each of those time points. So it's going to print t equals 1, d equals 1, t equals 2, d equals negative 0.7. I don't know. 0.64567. I don't know. And you should see a pattern of it going negative, positive, because the car is bouncing, and you should see that the bouncing gets smaller over time because it's a damped suspension system. Note that there is a cos function in cmath. There's an exp function in cmath, and you've got that built-in constant mpi that I told you how to activate with the pound define use math defines line at the top of your code. So work on that. Let me know how it goes. And until next time, good luck and happy programming.